All right, so our last topic was two-slit interference, and light rays from two different slits interfered and gave constructive and destructive interference at different angles. Now we're going to look at interference within the slit. Now the reason you'll get interference just with a single slit is as light passes through the slit, it's going to diffract, it's going to bend and spread around, and then light coming from, say, the top part of the slit can interfere with light coming from the bottom of the slit. So really, there's a lot of sources of waves in here. We'll introduce the variable A for the width of the slit. And now we're going to consider light coming from the top of the slit and the middle of the slit. And then here's our two light rays. We're in the far field approximation, so these rays are essentially parallel. And we're at an observation angle theta. Now, as we did for the two-slit experiment, we're going to drop a perpendicular here and argue that from here on in, these two rays are exactly the same length. So the path difference is just this little bit right here. And we want to come up with an expression for it. Notice that this length right here is just half the width of the slit. So I've redrawn this triangle over here. So here is half the width of the slit. Now, if this observation angle is theta, then here's the A over 2 side. That's half the slit width. If that's theta, this is the complement of theta, so this angle up here is also theta. And then this length right here, as we argued previously, that's the path difference between those two rays, top and middle of the slit. Now you're going to get destructive interference, and we're just dealing with destructive here right now. Destructive interference is going to happen when the phase difference is half waves. So when that's half wave, so that's m plus a half times 2 pi, because a full wave is 2 pi of phase. Now, the phase difference we showed previously was k times the path length difference. K is 2 pi over the wavelength. The path length difference is a over 2 sine theta. So that equals m plus a half times 2 pi. So the first minimum happens when this is 0. Then the 2 pi's cancel, the half cancels, and we get a sine theta equals lambda. That's the first minimum. That's when this point and this point cancel each other out. Now, it should be noted that if the very top and the middle cancel each other out, then if you move down a little bit, this point and this point will also cancel each other out because the geometry is identical. And so what happens is all the rays coming from the top half of the slit cancel all the rays coming from the bottom half of the slit. They will cancel each other out, and we'll get overall no light. You'll get a total minimum. Now that's called a diffraction minimum. Now if you remember, this is a little bit, it's something to keep straight. Our two-slit maxima, where we had constructive interference, we went through this derivation, and we arrived at d sine theta, where d was the slit separation, was m lambda. And so the two-slit maximum relationship looks a lot like the single-slit minimum or destructive interference relationship. It's just something we'll have to keep straight. Now, a similar derivation gives for the higher order minima, the higher order destructive interference. A sine theta is m lambda, so 2 lambda, 3 lambda, 4 lambda. Now, note in our derivation, m equals 0 didn't come out because the first minimum was at m equals 1. Okay? So lambda is the wavelength, a is the slit width. This is where you find the minima. Now, what about constructive interference? What about the two-slit maxima? Oh, I'm sorry, here, just quickly to show you where that relationship would come. So the way that you would derive it is you would divide the slit up into 4 parts here. So 1, 2, 3, and 4. And then you would consider waves coming from here and here as canceling each other out completely. And if that's the case, then waves from this quarter and this quarter will also cancel each other out. But now you've got, this is a over 4, and hold on a sec here. Wanted to make sure I had that right. So this is k. The path difference now is a over 4 sine theta, and when that's half waves, you'll again get destructive interference. So putting in m equals 0 to find the first place that these interfere with each other. 2 pi cancels, cross multiply the 4. 4 over 2 gives you a factor of 2 here, and you get a sine theta is twice lambda. That would be the next diffraction minimum. And so that's just to justify the statement that it's a sine theta is m lambda, where m is 1 and 2 and 3 and so on. Now, back to the bright spots and the constructive interference. Well, the argument that we just made isn't going to work, unfortunately, and finding the maxima is somewhat messy. The reason it's not going to work is if we divide the slit in half, and if we say, okay, this point and this point interfere constructively with each other, that's fine, okay? If they are in phase, then those two light waves will be adding together. But just because these two are in phase doesn't mean that this point and this point need to be, okay? So with cancellation it works, because if these two cancel, then these two are going to cancel. But it doesn't mean that that these 2 points here are going to line up in phase with these 2 points here, which they would have to get an overall maximum. So corresponding points will be in phase with each other, but not necessarily, it's not necessary that these points and these 2 points be in phase with each other. And actually, where everything does line up is slightly offset from what you predict from this argument. So maxima will have to wait, but we do have an expression for minimum. So just maybe I'll use color, that might be better. Okay, so the red points are in phase with each other. They'd have to be by the geometric argument. The blue points are in phase with each other, but the red points and the blue points don't necessarily need to line up with each other. Okay, diffraction. This is what diffraction looks like. You can actually see it in lots of cases. The edges are kind of blurry, and you see these beautiful fringes here. That happens as the light bends around the object and then interferes. This is actually an image captured with a camera of a safety pin. Okay? And you can see the same effect if you just pinch your 2 fingers together and then look at the light in the room. So you take your index and middle finger, pinch them together, and you should see fringes between them as you adjust the spacing between your 2 fingers. Okay, now we only see diffraction effects when when the slit width is comparable to the wavelength. Because if the slit is really, really wide compared to the wavelength of light, so that means that A is a really, really, really big number, then mathematically, using our expression for the first, or rather for the minimum, you'd get sine theta is m lambda over A. So if A is huge, so if you're dealing with the diffraction of light through a doorway, then sine theta is basically 0 and theta is 0. Similarly, if the slit width is exactly equal to the wavelength, then this side is just going to be 1 for the first maximum, m equals 1. Sine theta is 1 at 90 degrees, so that means that your first diffraction minimum, like if this was your single slit and this was your observation surface, it's going to be way out here at 90 degrees, so you're going to have a really, really broad peak in terms of intensity. So you only tend to see diffraction effects when these two are about the same order of magnitude and A is a little bit bigger, by a couple of factors over the wavelength. Okay, so what do calculations look like? Okay, that's just a comment on pinhole cameras. I might show you one in class. Let's see. All right, so here we've got light passing through 2 slits, and the slits have this much width, so that's the variable A, and then they're separated by this much. That's the variable D. And then we want to find the angles for the 2 slit maxima, so that's last class, 2 slit interference, and the angle for the single slit, that's this class, diffraction minimum. We find where those first 2 angles are. Okay, so that's the starting point of our calculation. Okay, our two slit maxima happen when the phase difference is full waves, so m times 2 pi m, and the phase difference, remember, is k delta path, and k is 2 pi over lambda, and the path difference for the two slit experiment was d sine theta. D was the slit separation. So this equals 2 pi m. You can cancel the 2 pi's and cross multiply, and then you'll get d sine theta is m lambda. So we're asked to find the maxima up to m equals 8. So that's actually the ninth order because it starts at m equals 0. So we're just going to put in 6, this is tedious, 7, 8. So we're going to put in those values of m and divide the wavelength by the slit separation. So since we want to find the angle, it's m lambda over d. I won't do the first one because putting in m equals 0 gives an angle of 0. Let's do the m equals 1 as an example. The wavelength is 650 nanometers. That's a 1 times that. And then the slit separation is 5.5 microns. So then we'll do the arc side of that, and we'll answer in radians. Okay, so when we do the inverse sine in radians mode, we get 0.117 rads, and then you could repeat that process for m equals 2, 3, and so on and so on. So we're still at about half a radian there. A radian's about 60 degrees. So we're certainly still on the screen there now. And then the last one is at 1.2 radians. So now we're getting out there. That's at around 70 degrees, right? So if our slits were over here, if this were our screen, that's 70 degrees. That's way, way up there on the screen. Next, the single slit minima. Now, for the minimum, the phase difference is going to be half waves. The phase difference is k times the delta path. In our argument, I'll have to go over here now, or maybe down here. In our argument, we divided the slit in half, so the delta path was a over 2 sine theta. And then for the first one, we let m equal 0, and we said that was half times 2 pi. And then cross-multiplying and canceling everything out, we got a sine theta was lambda. Then we went back to do the derivation, and we divided the slit up into 4, and so on and so on. We divided up into 6, and then we arrive at m lambda for the minima, destructive interference in the double slit. Okay, so if you want to find those angles, sine theta is m lambda over a. Let's do the m equals 1 as an example. And again, it's 650 nanometers. And what was the width of the slit? It is 1850 nanometers. So you do the inverse sine there, and you get 0.360 radians. And repeating the process for the m equals 2, you get 0.779 radians. So we're now going to draw the picture just to get an idea for what the overall observed pattern would be on the screen. So I paused there for a second and I drew the dots. So these would be the two slit maxima, the bright spots that you'd see on the screen. And they're fairly evenly spaced in angle. So here at 0, the slits would be lined up here, and then this would be straight across perpendicular to the screen. Then this is the m equals 1, 2, 3, 4, 5, 6 bright spots, and it carries on 7, 8, etc., etc. But what we want to notice is we're getting a minimum of diffraction at 0.36 rads, which is exactly where this third bright spot would be. And so that means that third bright spot isn't going to be there, okay? Because there's a diffraction envelope, diffraction intensity that is going to drop down to 0 at that point and just wipe out that bright spot so it's not seen. the diffraction intensity will pick up a little bit again, not as high as it was before, and then it's going to drop down again and wipe out that m equals 6 bright spot, because we see that there's a minimum of single slit interference at that point. 1, 2, 3, 4, 5, 6. On the other side, remember, it's symmetric. It's the same thing over here. So where are we here? Okay, there we go. That's not quite as good as my drawing at the top, but this should be symmetric on both sides. Should be like a mirror image. Okay, so this is called the diffraction envelope. Diffraction intensity. Okay, so that's what happens to the light intensity due to the interference within the slit itself, single slit interference. So now let's find an expression for the light intensity in this pattern. Now what we're going to do to start is we're going to treat this slit of width A as actually being a large number of single slits. And we're going to start then with our double slit relationship. So there's a slit here, and then we're actually going to go to n slits and see what that relationship is. So for two slits, we derived an expression that depended on the phase difference, like that, co-squared. Now, we didn't derive, but we can show that for n sources, the relationship becomes this. Note that for n equals 2, we expect to get back to our co-squared relationship. Let's just show that that actually works. If we put in n equals 2 here in the numerator, then the 2's just cancel. First of all, we get a factor of 4 here. And then we're going to have sine squared with n equals 2. It's just going to be delta phi. And then that's going to be over sine squared delta phi over 2. And then we can write this as a square. That's just sine delta phi over sine delta phi over 2, all squared. And then let's treat this as as sine 2x, where x is going to be delta phi over 2. So applying the trig identity, oh sorry, this should still be a 4. So this is now going to be 2 sine delta phi over 2 cos delta phi over 2 by the double angle identity. We notice that the sine delta phi over 2 term is going to cancel, and when I square the 2, so will the 4. And so then I'm going to arrive back at I naught. The only term that survives is cos squared delta phi over 2, which, as claimed, reduces to the previous. So at least this makes sense for n equals 2, and really it's just as we showed, you're just going to add up n phasors to arrive at this relationship. So for our single slit, we're now going to pretend that it's made up of n little n slits, and they are therefore going to be separated by a distance a over n, because a was the total slit separation. A was from there to there. And then the phase difference between those sources is going to be 2 pi over lambda times the path difference, and that's 2 pi over lambda times, I hate it when these things pop up, times this slit separation a over n times sine theta. And that just comes from adjacent slits, and then these being a over n apart, so it's just a over n sine theta. So now we use our n slit intensity relationship presented on the previous page. And so we'll have sine squared, and then it was n over 2 times the phase difference. So we substitute in the relationship that we just presented there, 2 pi over lambda a over n sine theta. And then we divide that by sine squared. And this is just going to be a half times delta phi. And we're going to introduce, for simplicity, the symbol alpha. And so this thing here, 2 pi over lambda a sine theta, is alpha. So this is going to be a little easier and faster to write. It'll be I naught over n squared. Then it'll be sine squared. The n's are going to cancel here, and so you're just going to have a half. So this will just be alpha over 2. And then down in the bottom, we've got sine squared. And here's the alpha, but the n doesn't cancel there. It's alpha over 2n. And what we're going to do now is we're going to take the limit as n becomes really, really, really big, because obviously we have an infinite number of sources in that small gap. So as n goes to infinity, we notice that in the denominator, it's the sine of alpha over 2n. As n becomes really, really, really big, that means the argument of the sine function is going to be really small. And sine x gets really close to x for small x. So first of all, let's write this as a limit as n goes to infinity. Why not? For n squared, so we had sine squared alpha over 2 over sine squared alpha over 2n. So we're going to replace sine squared of this just with itself. So this will be sine squared alpha over 2. And so this is just going to be alpha over 2n squared. So sine x goes to x, sine alpha over 2n goes to alpha over 2n, and so this, you just end up squaring it because it's sine alpha over 2n times sine alpha over 2n. And we still have to do the limit now as n tends to infinity. But now here in the denominator, the n squareds cancel out. And so we have just sine squared alpha over 2 over, this is going to be alpha over 2 squared. And now n's disappeared, so we no longer need to do the limit. I guess, yeah, we kind of don't need that limit there because we were kind of taking the limit of large n here to argue that sine of x was approximately equal to x. So I'm going to say that I've already taken that limit. And notice now, or just a reminder that what was alpha, that was just this expression here. It was 2 pi over lambda times a sine theta. Now, in the limit of really small alphas, so say as sine theta gets close to 0, sine theta will get close to 0, alpha will get close to 0, then this looks like sine x over x all squared. Now, the fundamental trig limit says sine x over x goes to 1, so that means sine x squared over x squared will also go to 1. And that means that at an angle of 0, that the intensity just goes to the maximum value as we get close to 0 degrees, which is good. And we notice as well that at higher angles that our intensity looks something like sine squared of this alpha term over alpha squared. And so if we wanted to graph that, it's kind of like sine x squared over x squared. So what does that function look like? Let's try and visualize that. So it ends up sort of being like a double slit intensity, except these peaks drop off. Why do they drop off? Well, they drop off because it's sine x over x squared, and over x squared drops off like this, right? So 1 over x squared, you know, it would have 1 over x squared, of course, would have asymptotes there. But when you multiply it by the sine x, the asymptote disappears. And so you just end up having something sort of like that as your envelope. So I'll just avoid that issue around 0. And then out here, this is kind of like 1 over x squared graphs. Okay, so it's going up and down and up and down and up and down, but then with decreasing amplitude. So the intensity decreases due to diffraction effects as you get further away from the central maximum. Okay, so that is an expression then for the single slit intensity. And this is going to pair with our expression for the double slit intensity. Let's do a quick example. So here we've got a single slit. Its width is 950 nanometers, and let's say we're shooting red light at it. So our diffraction relationship that we have derived says that the diffraction minimum, and I won't go through the phase argument, I'll just use the final result. The diffraction minimum are found at a sine theta as m lambda. So the m equals 1 minimum happens at an angle sine theta is lambda over a. So lambda is 700 nanometers. And then the slit width itself is 950 nanometers. So we do the inverse sine, and then we can find the angle at which that occurs. So just let me calculate that. Okay, so that, when you find the angle, let's just put the angle in the chart down here. So red light, 700 nanometer wavelength. So for the angle, it ends up being 0.985 radians. So that's really close to 60 degrees. So the angular width, you can see on the diagram, right? That's just the spread between these two minima. That's just going to be twice what this angle was. So that's about 1.97 rads. For blue light, you should be able to show that with a smaller wavelength, you get a smaller angle and therefore a smaller spread of that central maximum. Now we're also asked just to try out this new intensity relation we have at an angle of 20 degrees. So first of all, we work in radians just because it's a good sort of habit to get into. And we're going to be, if you're taking the sine of something, the thing inside better be in radians. That means your calculator has to be in radians mode. So we've got 2 pi here times the slit separation, which was 950 nanometers. Now the nano is just going to cancel out, so the 10 to the minus 9 is almost just an irritant. So the wavelength for the red light was 700 nanometers, and then we still need to multiply by the sine of the observation angle, 0.349. Now at 20 degrees, you see we're still pretty comfortably within that central maximum. Remember, this is about 60 degrees to reach that first minimum, right? So if that's 60 degrees at 20, you know, it should be fairly bright. We should see a fairly high intensity here. So we work this out, and this is going to have units of meters over meters or radians. So that's what we get for the alpha constant. So we have to divide it by 2. 2.91 divided by 2, and then square that, and then we have to take the sine of it and then square it, I should say. Then here we divide that by 2, and then we square this whole thing, and then that's the factor of that's the percentage of the maximum intensity at that location. So my calculation, I get 0.46 or 46% of that. So that's how the single slit intensity drops off. Now, of course, if we go back then to our double slit experiment, we say, you know, those slits really do have some intrinsic width. So the overall intensity then is going to depend both on the term that we had earlier for interference between the two slits, and now interference within the slit itself, right? The diffraction effect, the diffraction intensity. Now this is for 2 slits. For n slits, replace it with that big, ugly sine squared n over sine itself. And just a reminder that delta phi, this is 2 pi over lambda times d sine theta, and this alpha constant that we introduced is the equivalent corresponding to the width of the slit. So we really have these two functions multiplied together. So here was the two-slit interference pattern. It's cosquared. It just goes up and down and up and down and up and down. Here is the diffraction effect. It's like sine squared x over x squared, right? So there's an envelope function. It decays. And so the product of those two together, well, you get something kind of like this line here, where it goes up and down, but every once in a while, it drops down to 0. So it sort of chops the two-slit intensity down a little bit. And as we saw in some of our calculations, it means that there may be some peaks you expect to be in the two-slit pattern that aren't there anymore because they've been chopped down by this diffraction envelope. Now, we can do some calculations with that equation. These aren't the most intuitive things in the world, but let's just shine some light through a slit, and we know the slit width and the slit separation. So this is the width, this is the separation, and let's just see at an angle of 8 degrees what we get for the overall intensity. Now, we did this calculation before for this slit separation, and what we saw for that slit separation is we got a two-slit maxima at 0.117 rads and at 0.236 rads. So I just ran out of real estate there. Let's move it over a little bit. So we're kind of in between because 8 degrees is about 0.14 rads. So we're not expecting that this is going to be especially bright. So let's work it out. So first of all, we find the phase difference between light coming from the first slit and the second slit. So substituting in, so 2 pi d is 5.5 microns. Microns 10 to the minus 6 power. Sine 0.14, and then we divide by the wavelength. Wavelength is 650 nanometers, or 650 times 10 to the power minus 9. And so this gives us 7.49. We answer in radian units. Similar calculation for this constant gives 2.49 radians, according to my calculations. And so now we substitute in to the two-slit term and the single-slit term. So putting this angle in here for phi divided by 2 and taking cosine and then squaring it, I get a value of 0.67, so a 67% reduction. And then for the single-slit diffraction term, I get about 0.58. So together, it's about 0.39 of that maximum or original intensity. So the intensity is about 40% of its maximum value at that angular location. So that completes then a look at the light intensity relationship for single and double slit. In class, we're going to do a couple of examples related to diffraction patterns, and then we'll look at an interesting application to the eye, and we'll learn about angular resolution.